Largely due to the limited technology of the time, early PET applications were limited to neurology. Recent developments such as larger detector arrays, computers capable of processing large arrays of data, and improved pulse processing have made possible whole-body imaging, thus generating exponential growth in oncologic applications. Since cellular metabolic changes occur prior to morphological changes in anatomy, modern PET imagers transcend the limitations of the other medical imaging modalities and readily characterize the presence of disease. Due to their increased rate of metabolic activity, and because FDG is a glucose analog, FDG will accumulate in cancer cells, allowing visualization and an indication of their level of metabolic activity. Oncologists can rely on information contained in the PET image to base their clinical management decisions. PET and CT are thus complementing modalities in oncology. The detection is based on the annihilation of a positron, a positive beta particle, in fact a positive electron, and a conventional electron. This annihilation results in the emission of two 180-degree opposed high-energy 511 keV volts, or keV gamma rays. Recorded annihilations require the simultaneous detection of two 180-degree opposed photons. These photons must travel a distance equal to the system diameter within a time frame set electronically by the coincidence window. The coincidence window is thus specific to each system type. The next step in the detection process takes place in the scintillation crystal. Very high energy gamma rays, such as those arising from positron annihilation, require a crystal with a very high attenuation coefficient. There are four common scintillation crystals with an attenuation coefficient that have a useful sensitivity at 511 keV. They are 0.95 for bismuth germanate, or BGO, 0.37 for sodium iodide, 0.43 for barium fluoride, and 0.45 for cesium fluoride, or CSF. All things being equal, a sodium iodide system would require a crystal thickness of 77 millimeters to have the same sensitivity of a BGO system with 30 millimeters crystal thickness. Taking the 30 millimeter BGO crystal as 100% of sensitivity, we have for identical crystal surfaces a drop to 81% for 20 millimeter BGO systems, as used in some lower priced imagers, and only 42% for sodium iodide systems. These percentages do not reflect the increased scatter resulting from more rejected events by lower density or less deep crystals. The type and thickness of the crystals are of utmost importance in system sensitivity and the resultant whole body resolution. Since the lack of sensitivity can only be compensated for by longer acquisition times, any resolution gain will be lost to patient motion.